All right, as I threatened, here we have some more math with an ice table. Okay, ice tables are how you can determine or find the equilibrium position of an equilibrium. Given any set of starting conditions, you can find where the equilibrium is. So long as you either can solve some algebra problems or have a calculator that can do the hard work for you. Here we have an example of an ice table for the reaction AB plus CD. Going to, AB plus A plus B going to C plus D. Excuse me. So for this particular A plus B, C plus D, the A, the B, the C, and D, it's just 1 to 1 to 1 to 1. It makes it a little bit simpler to write it all out. And don't worry, I'll be doing plenty of examples, plenty of real examples. So hopefully you can learn this stuff. But in this hypothetical example, we start with 1 molar of A, 1 molar B, and no C or D. Okay. So that is the initial condition. That's what the I stands for, initial. And then we have our change. C is the change as we go from the initial condition to E, the equilibrium condition. So that's what I stands for, initial, change, equilibrium. So because it's 1 to 1 to 1 to 1, you lose X amount of A, you lose X amount of B, you produce X amount of C, you produce X amount of D. So the change is that A will lose X, B will lose X, C will gain X, D will gain X. Okay. If the coefficients were anything other than 1, then you would see different numbers there. It would be like minus 2x plus 3x, that sort of thing. And then we have our equilibrium condition, 1 minus x, 1 minus x, x, and x. And those numbers would be what we would plug into the equilibrium constant expression. So remember, KEQ is products over reactants. So C to the C times D to the D divided by A to the A times B to the B. And then you plug X, or those equilibrium condition values, into there. So X to the 1 times X to the 1 divided by 1 minus X to the 1 times 1 minus X to the 1, or X squared over 1 minus X squared. And then you solve for X. In this case, it's equal to KEQ is equal to 0.5, and it's not a particularly nasty quadratic equation to solve. So let's go ahead and solve it, why don't we? So here is our equilibrium expression. KEQ is equal to x squared over 1 minus x squared. That's, just C times D on the top over A times B on the bottom. And it's equal to 0.5, because that's the value of the equilibrium constant for this totally made-up thing. So the first thing we do to solve this is we move 1 minus x squared over to the other side of the equation. We multiply both sides by 1 minus x squared. That gives us x squared equals 0.5 times 1 minus x squared. Then we go ahead, we expand that expression, and we multiply 1 minus x times 1 minus x. Then we go ahead and multiply that by 0.5. When you've done all that, you get x squared equals 0.5 minus x plus 0.5x squared. Now, the quadratic formula only works when the entire equation is equal to 0. So what you have to do then is you bring everything over to one side. And that means, you subtract by both sides by 0.5, you add x to both sides, you subtract 0.5x squared from both sides. And over here, up top on the right, you'll see that gives you 0.5x squared plus x minus 0.5 equals 0. And that is what we are going to be plugging into the quadratic formula here. Negative b plus or minus the square root of b squared minus 4ac all over 2a, where a, b, and c are the coefficients of those three numbers up top. So a is 0.5, b is 1, and c is negative 0.5. So when you plug those into that formula, you get negative 1 plus or minus 1 squared minus 4 times 0.5 times negative 0.5. Do not forget the negative on that 0.5, or you'll get a completely wrong answer. All over 2 times 0.5. And when you multiply those out, collect your terms, you get negative 1 plus or minus the square root of 2 all over 1. So it's just negative 1 plus or minus the square root of 2. So negative 1 plus the square root of 2 is 0.414. And that is our actual answer. Now there is the other answer from negative 1 minus the square root of 2. That gets you a sort of imaginary, made-up, impossible answer, where you are able to sort of create negative matter and move even further to the left by, making negative products. But that's we're not going to consider that one. That one's just silly. So 0.414 is our actual answer. So what we do is we go ahead and we plug those numbers, or that number, I should say, that value of x, into our ICE table down there in the E line, the equilibrium line, so that we can double check and make sure that our work makes sense and gets us the right answer. So when you do that, you get that A's equilibrium value is 1 minus 0.414, B is 1 minus 0.414, C is 0.414, and D is 0.414. They're all molar, because it's concentration. And then you go ahead and, just for simplicity's sake, you do the math. A and B are equal to 0.586 molar each. And those are the four numbers that you plug back into the equilibrium expression. So KEQ is equal to 0.414 times 0.414 divided by 0.586 times 0.586. And when you multiply all that out, what you get is 0.499. And that is as close as needs to be to 0.5. That's just a rounding error. It's kind of unavoidable. And so we have, in fact, found the equilibrium concentrations of A, B, C, and D for this reaction. So just note that you can't predict in a super simple fashion what the values are going to be. The fact that KEQ is equal to 0.5 doesn't mean you have equal quantities of A, B, C, and D. It just it doesn't work that way. So let's go ahead and move on and look at a couple of real examples, why don't we? Our first example here is a 1 molar solution of vinegar, or acetic acid, which has a KEQ, an equilibrium constant, of 1.8 times 10 to the negative fifth. And that's a very small equilibrium constant. Vinegar is a weak acid, very weak acid. So the first thing we're going to do is we're going to set up our ICE table. Here's our equilibrium expression. Here's ICE, ICE. And the initial concentrations are 1 molar acetic acid, 0 molar H+, and 0 molar acetate. Now, this is a monoprotic acid. It produces only one proton. It only has one anion as well. So it's a nice simple 1-to-1-to-1 sort of reaction. So the changes are going to be minus X for the vinegar, plus X for the hydronium, and plus X for the acetate. giving us equilibrium concentrations of 1 minus x, x, and x. Now, I don't know about you, but I think that quadratic equations are time-consuming, major boring shit. So whenever possible, I want to try and avoid those. So I'm going to go ahead and make an assumption that x is going to be super-duper small. So small that it's not actually going to show up and affect the final concentration of the acetic acid. The acetic acid's concentration is essentially going to stay exactly the same. Okay? The x will be negligible. So let's just go ahead and erase that. Scratch it out. Ignore it. So now our equilibrium expression is KEQ is equal to x squared over 1 is equal to 1.8 times 10 to the negative fifth. Now we go ahead, we multiply both sides by 1. That gives us x squared equals 1.8 times 10 to the negative fifth, or x equals 0.0042 molar. You might recognize this number from a previous lecture. Now that we found this, before we assume everything is A-OK, nice and simple, yes, I love you, kitty cat, let's go ahead and double check, make sure that x actually is nice and negligible. And what we do is we just say 1 minus x. Is that going to show up at all? So 1 minus, or 1.0 minus 0.0042. When you do the math, you get 0.9958, and then you go ahead and, yeah, that rounds off to 1.0. Okay, it didn't have any impact. It was, in fact, negligible. So our assumption was good, and x is equal to 0.0042 is a perfectly valid answer. If I went through and did the math and did the quadratic equation, assuming that it wasn't negligible, then I would find that x is equal to something slightly different, but not different enough that we needed to care. But we're not done here. Okay? I didn't ask what is the final concentration. I didn't ask for x. What I asked for was, if you check back in the previous slide, what is the pH of 1 molar vinegar? So we're not quite done. What we need to do is we go ahead and plug that back in. Okay, so pH is equal to the negative log of the concentration of H+. Okay, so the concentration of H+ is x, or 0.0042 molar. So pH is equal to negative log of 0.0042, or pH is equal to 2.38. So, well, first off, there's our answer. The next thing I want to point out is that even though vinegar is a weak acid, it's not a negligible acid. Okay, it got us down to a fairly low pH. 1 molar is it's just a few grams of acetic acid. It's about 24 grams of vinegar in a liter of water. Okay, it's not a hugely concentrated solution, and yet it got us down to a pretty low pH. It's about maybe 1/20th the acidity of stomach acid. Okay, so it's not nothing. Okay, so being a weak acid, that is a relative term. Okay, so don't go nuts just saying that weak acid or a weak base is something you could ignore. It's not. You still need to be careful with it. All right, let's move on to our next example. And we are so close to the end of Chapter 13, I can almost taste it. But we are also so close to 15 minutes that I can taste it. So we're going to call it a day on this one, and I'll see you again in the next video.